So in section 3, we're going to take a look at the Cartesian plane and the graphs of equations. So we're going to look at a number of different types of graphs. By no means are we looking at all different graphs that we might do. We want to make sure that we want to know how to plot points in the Cartesian plane. This is the Cartesian plane with an x-axis and a y-axis. It's named after René Descartes, who's a French mathematician and philosopher. We want to be able to use the distance formula to find the distance between 2 points. We want to use the midpoint formula to find the midpoint of a line section. We want to use a coordinate plane to model and solve real-life problems. We want to be able to sketch the graphs of equations, find x and y intercepts of graphs of equations, use symmetry to help smooth the process of graphing by hand, and we also want to learn how to write the equations of and graph the graph circles. Okay, so when you think about the Cartesian plane, we've got a couple of different figures here to take a look at. It's a little weird in that you'll see that we go counterclockwise. So quadrant 1 is here, then quadrant 2, quadrant 3, and quadrant 4. And in quadrant 1, x is positive, right? X is positive, y is positive. In quadrant 2, x is negative, y is positive. In quadrant 3, x is negative, y is negative. And in quadrant 4, x is positive and y is negative. Okay, if we want to think about how we plot a point is an ordered pair. And an ordered pair has 2 components, the x or horizontal component and the y or the vertical component. Okay, so the x coordinate will measure how far to the right or left of the origin the item is, and the y coordinate will talk about how high above or below the origin the item is. Or you could think of it as the distance from the x-axis for the y coordinate and distance from the x-axis distance from the y-axis. So you could think of it as the distance from the y-axis would be the x-coordinate, and the distance from the x-axis would be the y-coordinate. And collectively they represent a move from the origin to a location on the graph. X would be right or left, and y would be up or down. Okay, if we want to look at plotting points on a Cartesian plane, we have x's and y's, so -3, 2, that's this point, -3, 2, 4, -2, 1, 2, 3, 4, -2 would be over here, this would be 4, -2, 3, 1, 1, 2, 3, and there's 1, this is 3, 1, and -1, -2 would be right there, -1, -2. Okay, so this should all be stuff you're really familiar with. Let me clean this up a little bit. So this was -3, 2. Okay, that's just plotting points on the Cartesian plane. If we want to take it a step further, we might want to deal with graphing pertinent information such as this. Now typically a graph like this, it would involve annual sales. Probably would only function in quadrant 1. But we'll go ahead and we'll plot this out. And what we want to take a look at, in fact I'm going to change off my grid and replace it with a grid that's a little more useful. So we'll go with this grid instead. I think it'll be a little more helpful for us. Because really what I want to do is I want to get a lot of flexibility around how I put my graph together and how I do my scale. So I'm going to work just in quadrant 1. And you can see 1, 2, 3, 4, 5. I may have a little trouble going, but I might go. Actually, if we do years since if our x-axis is years since 2001, then this would be 0 right here, and then 1 year, 2 year, 3 years, 4 years, 5, 6, 7, 8, 9, and right about here would be 10. Okay, but you'll see we're only going, right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're only going to go to 9. And then as I break up my scale here, they've said that these are in thousands of dollars, right, or sorry, thousands of customers. So y is times 1,000. And I'm looking here at the range. I go from a little under 200, and I'm going to go to about, oh, I don't know, looks like I'm probably going to go to about 268, almost 270. So one thing you can do with a graph, you'll see everything is going to be, if I started this at 0, everything with my graph will be way up here and it'll be a little difficult. So if I want to create an image of sort of a break, let's say I want to start at about 190. Sorry, my handwriting's looking a little poor at this moment in time. Let's try. Let's say I say that's 190. If I put a little zigzag in here, I'm showing that I've created a break in the graph. I'm not starting at 0, I'm starting at 190. Because then as I move up, I could go up by 5, so every 2 spaces would be another 10. So 90, 200, 210, 220, 230, 240, 250, 260, 270, and that's about what I figured out my range was going to be. So this is going to work out pretty well for me to put my items on the graph. So my first year was at 203.6, so it was just a little bit over 200. And then the first year since 2001, we were down to about 192 some odd. That would be about here. The second year, we were at about 205. That would be right about here. And then 220, here's 225, be a little above that, 226. And then the next year was 233, so here's 230 and under 235. And then 253, so here's 250, and right about there would be 53. 266 would be right about there. 268 would be up about here. And then it's going to go back down again, 249, a little under 250. Right about there. In my final year, basically right on 250. Okay, and this is what we would call a scatter plot. Okay, now scatter plots are useful, and in fact they're often the way things might be represented. I might use a scatter plot. Normally I'd use a scatter plot if I was going to try to do a line of best fit. And the idea of a line of best fit is that this isn't linear, but it looks really close to linear. And so I might say, oh, you know, I'm going to put in a value that approximates the annual sales, and I'm going to say it's like at about there. So I've sort of arranged my line of best fit through the middle of my data, and that would allow me perhaps to create an equation with which I could predict the future. Equally, we might put together, and what you might be a little more familiar with seeing would be like a bar graph of this data, where I'd put, you know, bars to show the relative sales year by year, something like this. So, and the tops of the bars would be where the scatterplot points were. So it just depends on who you're trying to show the information to and what you want to do. all we were trying to do right now was create a scatter plot, and I'm really sort of driving at what you might do after the scatter plot. Okay, so you should be able to do this, but bear in mind, what were the things I did? I took time to take a look at my the ranges of my values. I labeled my axes. I denoted that there was a break in my graph, that this was not going from 0 to 270. I was only looking from about 190 to 270. All this is about honesty and representing your material. Okay, now we want to look at the distance formula, and the distance formula is an offshoot of the Pythagorean theorem. So you're familiar with the Pythagorean theorem. If I have a right triangle, I know that the sum of the two sides squared will be equal to the hypotenuse squared. So I have a squared plus b squared equals c squared. And as you take a look at the idea about the distance between 2 points, when you look at this, if I say that this is side A, and this is side B, and this is side C, and I work with a squared plus b squared equals c squared, well, how do I know the distance here of side A? Well, it's the difference in my two y coordinates. So if I do y2 minus y1, that is A. So if I have that squared, and then I find this side, which is B, well, this distance is the difference in the x coordinates. x2 minus x1 would be B, and that would all be equal to c squared. And if I take the square root of either side, I'll get that the length of side C will be equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. And that is the distance formula. Okay, so the distance formula is a derivative from the Pythagorean theorem, and it allows us to calculate a diagonal distance between 2 points. Well, it could also be a vertical and a horizontal distance between 2 points, but that's so much easier that you really don't need the distance formula to do it. So let's look at using that if I want to find the distance between these points. The distance will be equal to the square root of the square of the difference in my x coordinates, so 3 minus negative 3, plus the difference of my y coordinates, 1 minus 0 squared. And 3 minus negative 3 is 6. 6 squared plus 1 squared. So this distance will be the square root of 37. So that's just using the distance formula. It's pretty straightforward, pretty easy. Now I can also use the distance formula to verify a right triangle, because I know at the end of the day that when I know the length of A and I know the length of B and I know the length of C, a squared plus b squared must equal c squared. So if I wanted to launch into a problem like this, I'd probably want to go ahead and sort of create a little bit of a sketch. In fact, I'm going to go over here and I'm going to grab a graph. And I'm going to drop it in here really quick. And I just want to sketch these points. So I'm at 2, negative 1, that's 1 point. And 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And 6, negative 3, here's 6, 1, 2, 3. And the idea is that we're trying to prove that this is a right triangle. Okay, so I know that this is 5, 5, and this is 6, negative 3. And this distance would be my hypotenuse. And over here I'll have 2, negative 1. So this distance is one side and this is the other. So if I start calculating distances, let's say A is this side here. I'm going to call them A, B, and C. So A will be equal to the square root of the difference between 2 and 5, that's 3 squared, plus 5 and negative 1, that's 6 squared. So this would be 36 and 9. A would be equal to root 45. If we take a look at B, B will be equal to the square root of the difference between this point and this point. So 6 minus 2 is 4 squared, and negative 3 minus negative 1, that's 2 squared. So B would be equal to 16 plus 4, that would be the square root of 20. And then when we look at C, C is equal to the difference between this and that, so that's 6 minus 5 is 1 squared. And negative 3, distance between negative 3 and 5 is 8. So it's going to be 64 and 1, this is going to be root 65. So if I put these together and say, well, is root 45 squared plus root 20 squared equal to root 65 squared? Well, yes, it is, because this squared is 45, this squared is 20, and this squared is 65. 20 plus 45 is 65, so this shows that this is a right triangle. Okay, the midpoint formula is a really simple formula. It allows me to find the coordinates of the midpoint of a line segment. So the point of a line segment that's halfway between the two ends. And all this really is that the x coordinate of the midpoint will be the average of the other two x coordinates. So I'll have negative 2 plus 4 divided by 2, that would be the average. And I'll have 8 plus negative 10, or 8 minus 10, over 2 for the y coordinates. Negative 2 plus 4 is 2. 2 divided by 2 is 1. 8 minus 10 is negative 2. Negative 2 divided by 2 is negative 1. So this would be the midpoint of the line segment that has these ends. Okay, so again, super easy to use. We often use distance and midpoint to find parts of conic sections, so they're an important part of creating different graphs. In this case, I've got a problem here. A quarterback is going to throw a pass from the 10-yard line, and he's 10 yards from the sideline. And the wide receiver is going to catch it someplace. So again, I'm putting in a little graph here, because what we want to do now is we want to think about how we are going to represent this for ourselves. So if he's on the 10-yard line, let's say that I make this the sideline, right? And so maybe we go 10, 20, 30, 40, 50. Maybe that's not how we would do it if we try to get the whole football field in the first quadrant, but this is enough for what we're doing. And let's say that these are yards from the left and right. So let's say that this is, I don't know, let's say that's 10, 20, 30 yards. Okay, so if we look at where is the quarterback, if he's on the 10-yard line, that would be here, and if he's 10 yards from the sideline, that would be about there. And his wide receiver is going to catch it on the 32-yard line, and he's going to be 25 yards, so that would be about here, and the 32 would be about there. And if we want to know how long is the pass, what we're asking about is what's the distance between these 2 points. So again, the distance would be, I'd find the difference in the x-coordinates and square it. So in this case, the x-coordinates were 10 and 25, so that's 15 squared. And the difference in the y-coordinates, so from 10 to 32, so that's 22 squared, and that will be my distance. So I'm going to want to pull up a calculator really quick, and I'm going to do 15 squared is 225. And 22 squared is 484. And if I want to find the sum of those things, I'm going to add them together, 225, and then I'm going to take the square root. So 26.63 yards. That's how far this pass was, 26.63 yards. Okay, if we wanted to take a look at something else, something similar here, when we talk about Yahoo, had revenues of 7.2 billion in 2008. So let's say, typically I would put time on the x-axis and I would put dollars on the y-axis. So let's say we have 2008 and 7.2 billion. And then in 2010, we have 2010 and we have 6.3 billion. So what would we estimate were the sales in between? Well, if you thought of this as a line segment, in 2009 would be halfway between these two. So I could say that in 2009, because that's the average between 2008 and 2010, I could do 7.2 plus 6.3 divided by 2, and I would be finding the midpoint. So this is 13.5 divided by 2. And so that's going to be 6.75, right? 6.75, about. That would be a reasonable estimate for what the sales were. Just sort of double checking, it's more than what we had here, it's less than what we had here, that's logical. Right? So here's how using midpoint to try to get an estimate of sales. That assumes that the sales were changing at a linear rate. If I wanted to go ahead and graph these equations, I might want to do, first I want to consider what type of equations are there. So these are quadratic functions. And what I normally want to do with a quadratic function is I want to find the vertex. And then I want to plot some points. Well, the vertex is related to the middle term when you think of ax squared plus bx plus c is equal to y. The x coordinate of the vertex can be found by doing the opposite of b over 2 times a. Well, b is 0. So I know that when x is 0, I will find my vertex. In this case, when x is 0, y is 3. 1, 2, 3. I probably want a couple other points. Maybe I'll plug in 1 and 2. So when x is 1, 1 squared plus 3. 1 plus 3 is 4. So that'd be here. And when x is 2, 2 squared is 4 plus 3 is 7. So 2, let's see, that's 3. So 1, 2, 3, 4, 4, 5, 6, 7. And I know that quadratic functions are symmetrical, so I can match to the other side. Equally, I could put in -1 and -2, but when -1 is squared, it becomes 1, and add it to 3, I'd be 4, right? And -2 would have an output of 7, and this is what my graph looks like. If I do that again with this item, 1 minus x squared, again, my b term is 0, so I know that x will be 0. 1 minus 0 is 1. This would be my vertex right here. And again, I'm going to plug in 1 and 2. Well, when 1 is squared, I have 1 minus 1, that would be 0. And when 2 is squared, I'll have 1 minus 4, that's going to be -3. 2, 1, 2, 3. And again, I'm going to use symmetry to match to the other side. And this is the graph of my other quadratic function. Okay, so I used information I knew about how to locate a vertex. I could have just done an input-output table with a lot of points, and I would have figured it out if I didn't remember this information. I remembered that they're symmetrical, so I use symmetry to match the other side of the equation, and we're going to talk about that a little later in this lecture. But I could have done it also with a graphing calculator. A lot of different ways we might have gone about this. If we just want to find intercepts, intercepts are where my graph hits the axes. So in this case, my y-intercept is y is equal to 0. You see I'm hitting it right here where y is 0. And I have two x-intercepts here and here, so x equals 0 and x equals -5. Those are my x-intercepts. Okay, so, and again, other ways I could find the intercepts. I did it by looking at the graph. I could do it algebraically by letting, to find the y-intercept, make x equal 0. So y equals the opposite of 0 squared minus 5 times 0. So y is equal to 0. And when I let y equals 0, that's the same as solving, right? -x squared minus 5x. I could factor this to be the opposite of x times x plus 5. And this would give me a solution of 0, and this would give me a solution of -5. And that's where I got my x is equal to -5. So I could do it algebraically. I could do it by reading the graph. It depends what information I've been supplied. We're going to talk about three different types of symmetry. I just talked about y-axis symmetry when I graphed the quadratic function. The y-axis is symmetrical when I have inputs that are opposites of each other, the outputs are the same. That happens when you're working with y-axis symmetry. So in this case, we're symmetrical around the y-axis. In the case of x-axis symmetry, we're symmetrical around the x-axis. So if I held up a mirror here along the x-axis, what I get below the graph looks like what I have above. Same here. What I have on the left side of the graph looks like what I have on the right. And when we're symmetrical around the x-axis, or around the origin, we're symmetrical around a diagonal line through the origin. And what we end up having is whatever's on one side is the opposite of what's on the other. Okay, so generally whatever happens on the right, you'll see the opposite happens here. If I moved x to the right and up y, then I'd move x to the left and down y. And these are ways to test by looking at the graph. So in this case, you'll see the x values are the same and the y's are opposites. When I'm symmetrical around the y-axis, the x values are opposites and the y's are the same. And when we're looking at being symmetrical around the origin, we have points where the x's and y's are both opposites. Okay, so y is the opposite, x is the same, y is opposite. X is opposite, y is the same, x is opposite, y is opposite. That's what we're looking at here for these. Okay, and the way I might test this is I can test an equation to find out what happens when I replace y with -y if I end up with the same equation. So if I take this equation and I replace y with -y squared is equal to 6 minus x. Well, the square of -y is y squared is equal to 6 minus x. You see I get the exact same equation. So in this case, this is symmetrical to the x-axis. Equally, if that had failed, then I might have tested by switching x with -x. And if that didn't work, then I might have switched x with -x and y with -y to see what happens. So, for instance, if I work with this, then I would also switch. If I wanted to test that with switching this with -x, we'd see that my y would be okay, But here I get y squared is equal to 6 plus x. This is not the same equation. Okay, and equally you can see that I also would have gotten 6 plus x if I'd done the second test. Okay, so this one fails, but that one works. Right, so different ways you can test for symmetry, and that really just helps you. If you're not sure, it helps you know how many input-output items do you have to do. Again, we're using a quadratic function. I'm just going to go ahead and draw in a grid here really quick, and I'm going to sketch it really fast. If I wanted to find my vertex again, I'd have the opposite of b over 2 times a, so that's going to be 0 again over 2 times 1. So that's going to be at 0 for my x-coordinate of the vertex. And when I do my input-output table, when I have x is 0, y is negative 4, so here's 1, 2, 3, 4. I might want to go ahead and really quickly find my x-intercepts so I could factor this. This is x plus 2 times x minus 2. So I'm going to have positive 2 and negative 2 as intercepts. Equally, though, I might have done that over here by plugging in 1 and 2. So 1 minus 4 is negative 3, and 4 minus 4 is 0. Here's that point. Here's this point. And I would have matching points on the other side of my graph, as I've already done. Okay, so when you know it's symmetrical, it just saves you, right? I only had to do points for the right half. I can match the left half up by using symmetry. Okay, these guys are a little different. They are symmetrical. You may not have graphed absolute value equations for a while. And if I want to do an input-output table here, you can tell, though, that one thing that's going to happen is this is going to all be positive, right? There's no way for my y necessarily my outputs to be negative numbers, right? So let's just plug in some numbers, 0, 1, 2. 0 minus 2 is negative 2, but the absolute value of negative 2 is 2. When I have 1, 1 minus 2 is negative 1. The absolute value of that is 1. And when I plug in 2, 2 minus 2 is 0, and the absolute value of 0 is 0. But if you think about what's going to happen as I move forward, what's going to happen when I move up? I'm going to do 3. And so let's plot these points. I have 0, 2. Here's 0, 1, 2. And I have 1, 1. And then I have 2, 0. And what's going to happen next is it's going to start going back up. And this is what the graph of my absolute value looks like. Because when I put 3 in here, this guy's going to be symmetrical. 3 minus 2 is 1. 4 minus 2 is 2. And there we go. Okay, and we're going to finish this up by working with one of the conic sections with circles. They're the easiest ones. Okay, when you look at a circle, we know that we have a distance called the radius that is from the center to any point on the circle. And you could see that if I wanted to find the value of the radius and I had to point on the circle, I would want to use the distance formula and find the difference between x and h, right? So if I had x minus h squared, I'd be taking the square root of this. And then I want to find the difference between y and k, so y minus k squared. So we found the horizontal distance, that's this length, and the vertical distance, that's this length. So we have a squared plus b squared, which would be equal to c squared, which would be the radius squared. Right? But I've square rooted either side and used the distance formula. And you see if I square both sides of this, I'll actually get the equation of a circle. So the equation of a circle is also a derivative of the Pythagorean theorem and is closely related to the distance formula. Okay, so if we want to use that, they tell me I've got a point, 1, negative 2, lies on a circle whose center is at negative 3, negative 5. So if I take my equation for a circle, x minus h squared plus y minus k squared is equal to r squared, I can plug these points in. So this is x, this is y, this is h, and this is k, because those are the coordinates of the circle, if you remember from our previous graphic up here. The coordinates of the center are hk, and then points on the circle would be the x and y. So I'm going to have 1 minus negative 3 squared plus negative 2 minus negative 5 squared will be equal to r squared. 1 minus negative 3 is 4 squared. Negative 2 minus negative 5 is 3 squared. So 16 plus 9 is 25 is equal to r squared. So now if I want to write the equation, it's going to be x minus negative 3, that's x plus 3 squared, plus y minus negative 5, that's y plus 5 squared, is equal to 25. Or I could write that as 5 squared, however you want to do it. Okay, so that's this section.